We are on Unit 9, this is Notes 5, and today we are doing trig substitution. Integration using trig substitution. So let's take a look again at where we've been so far with Unit 9. So far, we did a little review of all of our previously known integration techniques. Then we did integration by parts, integration using partial fraction decomposition, and the last time we looked at integrals of powers of trig functions. So today we're doing integration using trig substitution. So in this unit, this is our big integration unit, all right? So we are getting more and more tools in our tool belt to evaluate an integral. That's what we're doing all in this unit, all right? So by the end of the unit, we should have all of our tools that we know of that we can use. All right. So trig substitution is another tool that you can use for some sorts of integrals. Let's start by taking a look at something that we know. We already know that the integral of 1 over the square root of 1 over x squared, if we were given this integral, we recognize that this is in the form of arc sine. This is in the form of arc sine because inside the square root, which is in the denominator, we have an a squared minus a u squared, where u is some sort of x expression, right? And up on top, we either have the derivative of u or a form of the derivative of u, right? So a number if it's just a plain x squared term. Right? So this is just an arc sine, and this is our most basic arc sine, where this is just arc sine of x plus c, right? So we can't forget that, all right? So that's just arc sine. But what if we were almost in that form, but not quite? What if we had this integral instead? This is definitely not an arc sine because there's not a minus in here underneath, in between the two terms. So definitely not an arc sine this time. For this one, we need to use a different technique. And you might say, what about u sub? Well, if we let u be the 1 plus x squared, du is going to have an x in it, and we don't have an x up here. So we cannot use a u sub here. This is a great candidate for what we call trig sub, right? It's quite a bit like u sub, except we are going to be substituting in a trig expression for something in here, all right? So here is how you do trig sub. So first of all, it's a case of recognizing when you can use trig sub. And this square root is a great indicator, all right? If you have a square root of two terms, and it could be a plus or a minus, I could use trig sub on this one as well, all right? So it could be a plus or a minus, but the key is having the square root in the bottom, okay? So I'm going to come off to the side, and I'm going to say, all right, I'm going to use trig sub. No, you don't have to write that. I'm just doing that for your notes. All right, so we're going to use trig sub, and here's how it works. The first thing we're going to do is we're going to focus in on the square root of 1 plus x squared. And I'm going to form a right triangle, and that's going to be one of my sides. This is going to be one of my sides, okay? Since there's a plus inside, I know that that square root has got to be on my hypotenuse. If there was a minus inside, then I would put it on one of my legs, and it really doesn't matter which leg you choose, all right? But since it's a plus, I'm going to put it right here. Now, what does that mean our legs have to be to satisfy the Pythagorean theorem? One of the legs has to be a 1, and one of the legs has to be an x. I'll give you a little bit of a tip. If it's a number, if you have a number try to put it down on this, what is going to be the adjacent side. It doesn't really matter, but it might make a difference of using tangents and secants instead of cotangents and cosecants in our work. All right, so I try to put the number down here if it's an option. Sometimes it's not an option. That's okay. So that means x goes over here. Now this does satisfy the Pythagorean theorem, right? This is a true triangle because the square root of 1 squared plus x squared is right here. That's the hypotenuse. Okay? So I'm going to make this theta. All right? Making that theta. And now comes the substitution part. Right now, so far I've just drawn a triangle with correct values. These are just helpful correct values for this situation. So here's what I'm going to do. I would like to get a trig expression, cosine theta, sine theta, tangent theta, secant theta, a trig expression, a trig ratio for this square root. Okay? Now it's clear to me that for this square root, I need to use hypotenuse and adjacent, right? Hypotenuse and adjacent. So I can either use secant theta or cosine theta. Either one is fine. Secant theta or cosine theta. Because the secant theta is hypotenuse over adjacent. Cosine theta is adjacent over hypotenuse. All right? Now since I want just the square root of 1 plus x squared, I'm going to use secant theta. So I'm going to say secant theta is square root of 1 plus x squared over 1, right? So that's just 1 plus x squared. Now I have something to substitute in for this square root. So I'm going to be substituting in secant theta for that square root. Okay? So since I'm substituting thetas in for x's, I also must substitute something in for dx. I have to change that to something with a d theta. So I am going to use this. Usually whatever I use, I bubble. Now I need to get something to put in for dx. So now I'm going to go back to my triangle. Now I would like theta. I'd like something for theta. I don't want to use the square root. I only want to use the x and the 1 now. Preferably x over 1 instead of 1 over x. So since we have opposite and adjacent, I can use tangent here. I can say, okay, tangent of theta is x over 1, right? I want dx, so now I take the derivative of both sides, right? Take the derivative of both sides with respect to x, right? So secant theta, or the derivative of both sides. So the derivative of secant theta is, the derivative of tangent theta is secant squared theta, d theta dx, right? I'm going to be multiplying the dx on the other side, and this will be equal to 1, and now I'm going to bring my dx over. Okay? So secant theta d theta is equal to dx. So that I can substitute secant theta d theta in for dx. So my integral over here becomes 1 over secant theta times secant squared theta d theta. That's with all my substitutions. And now look what we have. We have the integral of secant theta d theta, and we know what the antiderivative of secant theta is. The antiderivative of secant theta is natural log absolute value secant theta plus tangent theta. That's something that you just have to know. Memorize it, flashcard, whatever you need to do, plus c. Okay? We are almost there. The only thing we have left to do is go back to x's. Now we have to go back to x's. So what can we substitute in for secant theta? Well, secant theta is hypotenuse over adjacent. Secant theta is the square root of 1 plus x squared. That's what we have there, right? What is tangent theta? Tangent theta is x over 1. And that's our answer. So you can always check these, right, by taking the derivative of this, and we should get back that. Okay? Oh, not that, this. That was our previous problem. Okay? We should get back this. All right. What do you think? So it's another kind of substitution. We're just substituting a trig expression with theta in place of an algebraic expression with x's. Okay, let's try another one. Let's try the integral of the square root of 9 minus x squared dx. Okay, again, you might think u sub, but if u is 9 minus x squared, du would have an x in it, and we don't have an x out here. If we did, that's exactly what we would do. We would just do a plain u sub. But we don't, so we have to do something else. Okay? So, we will. Let's come off to the side and do trig sub. Now, why trig sub? Because the square root, and then 2 terms in here. Plus or minus, it really does not matter. Okay? Plus or minus does not matter. Okay, so I'm going to come over here and use trig sub. So I'm going to draw a triangle so that I can see where everything goes. Okay, this time there's a minus, so this square root will not go on the hypotenuse. You can choose either leg to put it on. Okay, I like to just let my opposite leg always be x, just like we did up here. I like for my opposite leg to always be x. Okay, so that makes this leg the 9 minus x squared. All right, and that will make the hypotenuse has to be a 3 here, because that's the positive number. And so to make Pythagorean theorem work, this has to be the 3, and that has to be the x, if I put the square root of 9 minus x squared down here. So here's my theta. So we come off to the side. So I'd like an expression just for the square root of 9 minus x squared. So let's take a look. Here's my theta. I'd rather not use the x. I'd rather use the 3 and the square root. So I'd rather not get the x involved quite yet. So since I have the square root as the adjacent and the 3 is the hypotenuse, this time I'm going to use cosine. I'm going to say cosine of theta is adjacent over hypotenuse. And since I want just the square root, I'm going to multiply both sides by 3. So there's the first thing that I can use to substitute in. So in place of the square root of 9 minus x squared, I'm going to put 3 cosine theta. If we had switched these, we would have a sine here instead of a cosine. Then that's fine. All right. Next up, we need to substitute in place of the dx, right? So now I'd like a trig ratio that involves the x and the 3. So now I don't want to use this square root because I want to keep it as simple as I can. So I'm going to use sine, because sine of theta is x over 3, opposite over hypotenuse, right? Which means 3 sine theta is equal to x. Now take the derivative of both sides with respect to x. So we'll have 3 cosine theta d theta dx is equal to 1, but now I'm going to multiply both sides by the dx. So there is what I can substitute in place of the dx. So now we're coming back over. In place of the square root of 9 minus x squared, I'm putting 3 cosine theta. In place of dx, I'm putting 3 cosine theta d theta. So this gives me 9 cosine squared theta d theta. And we learned yesterday how to handle that. I'm going to bring the 9 outside. For cosine squared, we have to change it to the identity with the 1/2s in it. 1/2 plus 1/2 cosine 2 theta d theta, right? So the antiderivative will be 1/2 theta plus, all right, this will be 1/4 sine 2 theta plus c. Now we have to go back to x's. What can we put just in place of theta? What can we put just in place of theta? Here's what I do. I come over and look at what I have already. Okay? I could use this. I could use this. I could use tangent, I could use cotangent, I could use any of the ratios that involve, I can use anything that involves the x. Okay, so these all will involve an x. So I'm going to go right here to 3 sine theta. Actually, I'm going to go right here. And I'm going to solve that for theta. How can we solve that for theta? Theta is equal to arc sine x over 3, right? So this is now 9/2 arc sine x over 3. Okay? Now we have this sine of 2 theta. Well, that's a problem because we don't know much about 2 theta. I need to use my identity for sine of 2 theta to go back to sine theta and cosine theta. So the identity, sine of 2 theta is 2 sine theta cosine theta. And that's something that I can come over here and get, right? So we're going to have 9/2 arc sine of x over 3 plus 1/2, right? Sine of theta. Sine of theta is x over 3. Cosine theta, and cosine theta is this expression. So square root 9 minus x squared over 3 plus c. And that would be a safe stop spot, right? Otherwise, we would just multiply these together. Okay? All right. So that was a little bit, the trig sub was fine. It was just getting back to x's that was a little bit of a struggle, especially if you are not super comfortable with all the trig stuff quite yet. But hopefully after this unit, you'll be a little bit more comfortable with that stuff. Okay, let's try another example. In your notes, this is example 2. That very first one that we did was just a little bit of an introduction. Okay, let's look at this one. Negative 12 over x squared square root 9 minus x squared dx. This is not an arc sine because of the x squared out here, right? And we cannot do a u sub because we would have u be the 9 minus x squared. Du would have an x in it, and that x would have to be on top, right? So this is not a u sub. It's not an arc sine. It's not an arc secant. This is another good candidate for trig sub because of that square root. Because of that square root. Okay? So, trig sub. I'm going to draw the triangle. again, I'm focusing on the square root. I want that square root to be one of my sides. Since there's a minus, it's going to be one of my legs, and it really doesn't matter which. Again, I think I'm going to make it be the bottom leg, the adjacent leg, so that I can let x be that side. X is that side, right? And then the hypotenuse has got to be a 3 because it's the positive number inside that square root. So here is my theta. Right. So first of all, we're trying to get something to substitute in place of the square root. So I'm going to involve the square root and the 3 again. So that's going to be cosine. Cosine theta is the square root of 9 minus x squared over 3. So 3 cosine theta is the square root of 9 minus x squared. So I found what I can substitute in for the square root of 9 minus x squared. Now I need to substitute something in for x and dx. So now I'm going to make it my trig ratio involve the x and the 3. So I'm going to use sine. So sine of theta is x over 3. So 3 sine theta is x. Okay? So now I know what I can put in place of the x squared. 9 sine squared of theta, right? I still need dx, so I'm going to take the derivative of both sides with respect to x. I'm going to have 3 cosine theta d theta dt, I'm sorry, d theta dx is equal to 1, and now I'm going to multiply by the dx, right? So now I have something to put in place of the dx. I forgot to bubble this one. That's what I'm putting in place of the x. So I have all 3 things to sub in. So back to my integral. The negative 12 I could pull out. I think I probably will next, but for right now I'll leave it in there. So in place of the x squared, I'm putting 9 sine squared theta. 9 sine squared theta. In place of the square root, I'm putting 3 cosine theta. And in place of the dx, I'm putting 3 cosine theta d theta. Okay? So what happens here? Some nice things happen, don't they? The 3 cosine theta and the 3 cosine theta cancel out, and the 12 and the 9 reduce, and then I'm just left with negative 4 over sine squared, and that is negative 4, which I'm going to pull out, cosecant squared d theta. Do we know a trig function whose derivative is cosecant squared? Yes, we do. Cotangent, right? Negative cotangent. So this would be negative 4 times negative cotangent theta plus c, which is 4 cotangent theta plus c. So now we just have to go back to x's. So here's theta. What is cotangent theta? Cotangent theta is adjacent over opposite. So square root of 9 minus x squared over x plus c. And I just realized I didn't bring over that 3, did I? I need that 3 out front, that 3, that over 3, over 3, over 3. So there you go. That's a little bit better. Well, this is more accurate. This is accurate. Yeah, I just forgot to bring that 3 over there too. All right. Example 3. It's where I need to be in class, and you guys can tell me, oh, you forgot that 3. And I'll say, oh, you're right. Okay, next up, x over square root 9x squared minus 1 dx. Okay. Well, in this one, I always look at u sub first, you guys. I always look at u sub first. If we let u be what's inside the radical, du would have an x in it, and look what we have. Like a gift from Santa Claus, we have an x up there. So in this one, we don't have to use trig sub. We could use trig sub, but we don't have to. We can just use a plain u sub. U is the 9x squared minus 1. Du is 18x dx. So in place of the x dx, I can put 1/18 du. And then I would have 1/18 integral u to the negative 1/2 du. And now it's just a power rule. So 1/18 times u to the 1/2 times 2 plus c. Go back to x's. And we're done. But we certainly could have done something similar to this up here and used trig sub for that, because it does have the square root and an x expression and a number. It needs to be an x expression and a number in either order. Okay? All right, number 4. I wonder if I can fit this. I think I'm not going to try to squeeze. I'm going to just go to another piece of paper. So example 4, last example. 1 over x times the square root of 4x squared plus 1 dx. If we did a u sub, du would be 8x. Do we have an 8x to use for a u sub? No, we don't, because the x has got to be up on top to do the u sub with it. There's an x down here, but that is unhelpful. We need it to be up here. So this is not a plain u sub. So we're going to use trig sub because of that square root. So triangle time. There's my theta. Okay, there's a plus in here this time. So that has got to be the hypotenuse. These don't matter, either one. Again, I like to keep this adjacent side my constant if I can, which makes this side 2x in this case, right? So that's what I would do, but you can do either one. Again, it's just a matter of would you rather use secants and tangents or cotangents and cosecants? You can do both, or you can do either. All right. Okay. We need something to sub in for x. We need something to sub in for that square root, and we need something to sub in for dx. So let's start. I like to start with my square root. So I'm going to use secant because I can use adjacent over hypotenuse. So secant of theta is the square root of 4x squared plus 1 over 1. So that's it. So in place of the square root, I'm putting secant theta. Now in place of the x, I'm going to use opposite over adjacent. So that's tangent. Tangent of theta is 2x over 1, right? So 1/2 tangent theta is equal to x. And that's what I can sub in for x. Now I need something to sub in for dx. So I'm going to take the derivative of both sides. I'll have 1/2 secant squared theta d theta is equal to 1 dx. And that's what I'm going to sub in for dx. Come back. Okay, in place of the x, I'm putting 1/2 tangent theta. In place of the square root, I'm putting secant theta. In place of the dx, I'm putting 1/2 secant squared theta d theta. Okay, the halves cancel out. One of the secants cancel out. So then I have the integral of secant theta over tangent theta d theta. And now it's just a matter of what do I do with that. Okay, now we go back to the last section. What do we do with that? Secant theta is 1 over cosine. Tangent theta is sine over cosine, right? So if we multiply by cosine over cosine, it's going to be very helpful, because secant theta times cosine theta is 1. Tangent theta times cosine theta is sine theta. Now we just have cosecant theta, and we know the antiderivative of cosecant theta. It is negative natural log absolute value cosecant theta plus cotangent theta. Again, just got to know those. Just got to know those. Okay? Plus C. And now we just go back to x's. So what can we put in place of cosecant theta? Cosecant theta is hypotenuse over opposite. So square root 4x squared plus 1 over 2x plus cotangent theta is adjacent over opposite, so 1 over 2x. And that's great. They might make a common denominator here. They might change this to 4x squared plus 1 all over 2x. What else could they do here? With this negative out front, they could make it the exponent, which would flip this whole thing. So either one of those. This would be the safe stop spot right here. Okay, but be able to manipulate just in case it's a multiple choice question, right? Okay, I hope you like trig sub as much as I do. I find it so interesting to be able to substitute something else instead of just a u, right? Or a v, or a dv, right? So it's a fun thing to do. So go and practice and see what you think. See what you think.